Have you ever thought about your college library, but scaled up to millions, maybe billions of books? Now picture all those books just chucked into one massive, chaotic pile. How on earth would you find the one specific book you need for your exam tomorrow? It sounds impossible, right? Well, guess what? A database does this kind of thing billions of times a second. It's the magic behind pretty much everything you do online. So let's pull back the curtain and see exactly how they pull it off.
So for this explainer, we're going to go on a little journey together. We'll start in that big, messy pile of data, the chaos. Then we'll bring some order to it with something called file organization. After that, we're going to give our database a genuine superpower called indexing. And finally, we'll peek under the hood to see how these indexes actually get the job done.
Okay, first up, let's talk about data chaos. I mean, we all use folders on our laptops to keep things tidy, so what's the big deal? Well, here's the thing. When you're dealing with the insane amount of data a modern app handles, that simple folder system it completely falls apart.
And this is where things get really interesting. On one side, you've got the old-school file system. Think of it like every department in your college keeping their own separate Excel sheets. You get tons of the same data copied everywhere, sharing is a pain, and if a computer crashes, poof, that data could be gone for good. But a database management system, a DBMS, is a whole different beast. It puts everything in one place, cuts down on duplicates, makes sharing a breeze, and has your back if things crash. It's a total game changer.
So, that brings us to the very first step in taming all this chaos, file organization. Before we can find anything fast, we have to decide how we're going to store it in the first place. It's like before you even put a single book in a new library. You have to decide, are we organizing by author, by subject, or maybe by the year it was published? Right, so here's the key idea. File organization is literally the blueprint for how your data physically sits on a hard drive or some other external storage. We're not just talking about files here. We're talking about how every single record gets grouped into blocks and where those blocks are placed. This one decision, right at the beginning, affects everything else down the line. Okay, so let's check out two of the most basic ways to do this. First, there's sequential file organization. It's simple. You just add new records one after the other, kind of like lining up books on one really long shelf. It's easy to add a new one at the end, but finding a book in the middle means you have to walk past every single book before it. Then you have heap file organization. This one's even simpler. Just toss the new record into whatever space is open. Super fast for adding data, but searching? Oh, it's a total nightmare. You have to check the entire pile every single time. So you can see the problem, right? These basic methods are fine for some things, but they are not fast. They're not going to give us that split-second response we expect from our apps. So that brings up the big question. How do we get faster? A lot faster.
And the answer is a superpower called indexing. If file organization is about arranging the shelves in our library, indexing is like creating a magical, perfectly detailed card catalog, one that tells you exactly which shelf and which spot on that shelf to find any book you want instantly. So, what is indexing, really? Well, it's a clever technique that lets us find data incredibly fast. Instead of having to scan through all the data from the beginning, like reading a whole textbook to find one definition, you just look at a much smaller, highly organized index. That index gives you a direct pointer, a shortcut, to the exact physical spot where your data lives. And that is the secret sauce that makes everything feel so instantaneous. Now, not all indexes are created equal. A primary index is the big one. It's built on the primary key, something unique, like a student's roll number. And here's the kicker. The actual data on the disk is physically sorted based on this key. Because of that, you can only have one. But then you have secondary indexes. These give you a lot more freedom. You can build them on other columns, like student name or city, to make searches on those fields faster too. And you can have a bunch of these. This leads us perfectly to the idea of a clustered index. You can think of this as the database's version of a primary index. It's so special because it's not just a separate map, it actually dictates how the data is physically sorted on the disk itself. It is the main organizational system for the whole library. And just like you can only sort the books on the shelves in one specific way, you can only have one clustered index for each table.
Okay, so we know what an index is, and we know it's a superpower. But what's actually going on under the hood? How does it all work? Let's get into our final section and look at the two main ways databases build these amazing structures.
First up, we've got hash-based indexing. And honestly, this is just pure mathematical magic.
It uses a special formula called a hash function. You take your key, like a student ID, run it through this formula, and boom, the answer it spits out is the exact physical address of your data on the disk. No searching needed.
So the process is beautifully simple. You give it a key, it gives you an address. This makes it unbelievably fast for finding an exact match, like searching for a student with ID number 1-2-3-5. But, and this is a big but, it has a major weakness. Because that hash function is designed to scramble things up, it's totally useless for range queries. It can't help you find all students between the ages of 18 and 21.
So if hashing is the super fast specialist for exact matches, what's the alternative? Well, that brings us to the real workhorse of the database world, tree-based indexing.
So instead of a direct math problem, this method organizes everything in a tree structure. You can kind of think of it like a family tree. You start at the top, the root, and you navigate down the branches based on the value you're looking for, making a choice at each level until you find your data. This structure is amazing, not just for finding one specific thing, but also for grabbing everything within a certain range.
A classic example of this is something called ISAM, which stands for Indexed Sequential Access Method. It's a really clever way of combining the ideas we've already talked about. ISAM takes a file that's already sorted sequentially and then builds a separate, smaller index file right on top of it. It's the best of both worlds.
Let's just walk through why this is so cool. First, your main data file is kept neatly sorted, which is awesome for things like generating a big report. Second, that separate index acts like a shortcut, like a roadmap. So instead of reading the entire massive data file, the database just reads the tiny little index to find out where to go. And that makes searches incredibly fast. You get the benefits of sorted data with a super quick lookup system.
All right, time for the showdown, hash versus tree. Here's the simplest way to think about it. Hash-based indexing is your specialist. It's like a sprinter who is absolutely unbeatable in the 100-meter dash, which is your exact match query. Tree-based indexing, on the other hand, is your all-rounder. It's the versatile athlete who is great at all sorts of things, especially those range queries. That versatility is why it's the foundation for so many databases we use every single day. And really, this all boils down to one absolutely critical point. And it comes straight from the source material. There is no single best way to do this. There's no magic bullet. The right choice of how to organize your files and what indexes to use depends completely on how you're going to access your data. Are you doing exact lookups, range queries, lots of new data coming in? The answers to those questions determine your design.
So we've gone on this whole journey from a giant, messy pile of records to a super smart, searchable library. I'll leave you with a question to chew on. If you were designing your college's student database and you knew you'd need to look up a student by their exact roll number, but you'd also need to find all the students from a certain city or in a certain age range, which indexing methods would you use and on which columns? That's where the real engineering begins.